Hi, this is a short video about derivative and optimization, and the goal is to remind you of the meaning of the derivative as a slope of the curve, and to remind you of how to use the derivative to optimize a function. So I somehow assume that you've seen these things before, so I will definitely skip some details or be a bit fast if it's new. It would be fast if it was new. So we're going to talk about this in the case of this example. Suppose you have this problem of a function g defined like this, and you'd like to know for which x does this attain a maximum or a minimum. So you can have a look at the graph, and this is a rough sketch. And from it we can see that there should be some maximum here, minimum there, maximum there, and we'd like to compute this precisely. And that's where the derivative comes in. But before we do this, let's remind you of what the derivative is and what it has to do with slope of a curve. And we do this first for another example. Suppose you have a different function f of x, and it's simply the sine of x. And you know what it looks like, I do hope. It starts off a bit like that. And suppose I'd like to know the slope in this point. Well, what do I mean by a slope in a point for a curve? It's defined through the tangent line. So we can draw a tangent line to this curve here. And then actually the slope of the tangent line is by definition the slope of the curve in this point. And how do you construct the tangent line? Now I just put it there immediately correctly, but you could also do it in a procedure of steps, taking what they call second lines, lines that still intersect the curve in 2 points, like this. Of course, the slope of this one is not the same as the slope of the tangent line, but as I choose this point closer and closer to the origin, there will be an approximation of the slope of the tangent line, and this second line will transit into a tangent line. Okay, so there's some of approximation procedure, which will translate into a limit that we discussed in the previous video, and there's the notion of slope of a line. Well, the slope of a line we know how to compute. We just need the change in the x and the change in the y. So there will be a delta x here, and there will be a delta y there. And let's see. So delta y divided by delta x, that's what the slope is. And of course, here we're at the function itself, so that will be in this case the f of a, let's say that's the point A, minus the f of 0 divided by, if this is A, then of course the delta x will be equal A equals A minus 0, I could write. So what we get here is the sine of A divided by A. So that's the slope. And now for the limit procedure, so the derivative of this function f at 0 will be the limit where this a now goes to 0 of this slope of the sine of a divided by a. And fortunately, this was exactly the limit we discussed in the previous video, so we know it's 1. And then we can see how terrible this drawing was, because it definitely looks a bit steeper than that. The computation tells us the slope is 1, and therefore the derivative. But this is the derivative for just a point, so it's not exactly yet a function. So generally, maybe you could do this for any point and find that the derivative function in x would be the cosine of x. But we're not going to look for at this example. We're going to take a slightly easier one. Another example will be h of x is x squared. And now we're going to compute, so clearly the curve is a parabola, and now we're going to compute the derivative in any point. So in that case, again, we need to take a limit. And again, we have a point A on the curve. And now for any point, we want to compute the derivative h of x, h prime of x in any point x. So the role of 0 is now changed for x in general. So it's the delta y divided by delta x will be the age of a minus the age of x divided by a minus x. All right, can we compute this? Yes, we can. Let's fill it in. You get the limit of a goes to 0 for a squared minus x squared divided by a minus x. And of course we know the top one is actually can be decomposed. I'm writing a goes to 0, but that's of course wrong. In this case, the role of 0 was going to be replaced by x, so it's a goes to x. Sorry about that. So there you go. It's a minus x times a plus x divided by a minus x. And there you go. So it's the limit of a goes to x of a plus x, and that is going to be 2x, which hopefully looks familiar as indeed the derivative of x squared. And this tells you, I want to repeat this, this tells you for any value of x what the slope of the tangent line is at the point x comma fx, or in this case hx. So that's sort of nice because we can apply this when we want to optimize, when we want to find the extreme values of this function with this graph, because that's exactly when the slope is 0. At least these are what they call the stationary values, and these are potential extreme values, because of course it could be horizontal for a little bit and then continue to grow. But in our case it looks better. It looks like any stationary value is indeed an extremum. So stationary value of f, that's exactly when f prime of x is 0. So that's a stationary value x. So let's compute them in this case. That means we have to compute the derivative of g. Okay, so for there's a few rules about differentiation that you need in this case, because there's a product of two functions here, and then the sum with two other functions. So we're going to use that the sum of different functions have as a derivative the sum of the derivatives of those functions, and we're going to use the so-called product rule. So let's start off with that product rule. It tells you that the derivative of this product is the derivative of the first function, which is 1, times the second function, plus the first function times the derivative of the second function, which is the cosine of x. Then here we have the derivative of the cosine of x, which is minus the sine of x. And there we have the derivative of the sine of x, which is the cosine of x. So let's see, this should simplify a little bit, because here I have sine of x and minus sine of x. So this is actually x times the cosine of x plus the cosine of x. And maybe for future purposes, I write this as x plus 1 times the cosine of x. Then for stationary values, we have to say, well, suppose g of prime of x equals 0, right, for stationary values. If this is the case, it means that x plus 1 times the cosine of x equals 0, which means x equals minus negative 1, or And within the domain, the cosine is 0 only on plus or minus pi over 2. So indeed, these are, and it sort of fits our picture here, my -1 and negative pi over 2 and pi over 2. So I am confident that this computation is all right. And so to conclude, the goal of this video was to show you what was the meaning again of the derivative. It's the slope of the tangent line at a point. We see how the limit comes into this definition, and then we've applied it to solve an optimization problem by looking at what values of x the derivative equals 0. And we had a quick reminder of that we need some techniques like the product rule, sum rule, to compute derivatives. So I hope it helped you on your path towards refreshing all your mathematics.